All right, we're live, we're recording. We're going to talk about E. And, okay, so what is E? Well, E is a number. And I'll get to that question later. Okay, so E is a number. And like any number, it can be represented by a symbol. The symbol for pi is always 3.14159.265, blah, blah, blah. That's as far as I remember it. The symbol E represents the number 2.7182812. This looks like it's repeating, but it in fact isn't. That's just coincidental. It is in fact, just like pi, irrational, which means its decimal would never terminate or repeat. Now, where does the E number come from? Everybody understands, at least basically, where pi comes from, right? It comes from geometry. E can't be defined geometrically. Hopefully everybody watched the little video about E that I put, the YouTube clip that I linked to on my blog. But as a really quick kind of refresher on that video, and just as a quick reminder, what makes E so darn special is that E, here I am making a graph of y, or function of x, is e to the power of x. So think about, compare this to, like, for example, y equals 2 to the power of x, right? That's just your basic exponential function that it goes through, it goes through 0, 1, and then, 2 becomes 4, 4 would become 16, etc. So it's 2 to whatever power. 2 to the power of 3 makes 8, right? So there we go. So there's the thing. So this is just a typical exponential function, but the base, instead of being 2 this time, the base is this weird number e. And what's really cool about it is, or two things that are really cool about it, is that firstly, if I put the point, and I just did here, let's label it, if I put the point where x is 1 on here, I get e to the power of 1, which is e, right? If I take the slope of this thing at that point, notice that the slope is also e. If you're wondering how I got the slope calculated, remember m stands for slope, and you're going to learn in calculus that you can do something called a derivative, which is what I just did here. But trust me, the slope at this point is the same as the y coordinate. And that's true everywhere on the line. That certainly wouldn't have been true for this thing. If I wanted the slope at this point, it would not be 4. As a fact, you can totally tell it's going to be less than the slope here, and this slope was 2 point something, right? And moving along, the slope at this point will not be 8. There is, in fact, only one base out of all the numbers you could possibly use as a base in this kind of a graph where it's true that the slope at that point is the same as the y value. And we can kind of show it to you. If I slide that point along, like say I slide it to 2, notice that's exactly 2 times e. And if I slide it to 3, I will get exactly 3 times e for my slope. Isn't that nifty? That is not something that any other function will do. And on top of that, as if that wasn't cool enough, let me get that slope line out of the way. If I were to take, here again I have the value where x is 1. If I were to drop a line straight down to here and shade in that area, and keep in mind this area does go on forever. I know it looks like these two lines touch, but in fact they don't. It's an asymptote. It just gets infinitely close. So if I add up all of the area straight down here to the left, that area would exactly equal e. And if I shifted a over to where x is 2, and I get e to the power of 2, which is 2 times e, this would be the area 7.39, or 2 times e. And if I moved up to 3, I'd get 3 times e. So the slope and the area at every point is the same as its y value, which is really cool. Certainly blew my mind the first time somebody showed me that. And that's what's so special about it. It pops up in so many places in nature, just like pi pops up in just about everywhere you can think about geometrically. E pops up just about anywhere that you come across growth, and exponential growth especially. Now, because e is such an important number, we have our own notation, a special notation for when we use it as a base of a logarithm. So instead of saying log with a little e, so instead of saying log to the base e, we just say ln. And that's the way we pronounce it. We say ln, as in like lawn. Okay? So ln 5/3 is the same thing as saying what's the log to the base e of 5/3. And on your calculator, it will have its own number. Okay? So actually, I guess maybe before we do that, we should, oh yeah, I guess I got rid of the graphs, right? We're not going to play with graphs other than that. All right, so let's find that number. So let's see. Let's go ln to the base. Okay, now you're in the way, calculator. So let's go clear on. There we go. Clear everything. And let's go natural log. And it opens, my calculator opens a bracket for me. If yours doesn't open a bracket, so you can go 5/3, close your bracket if you have to, and then hit, and then there you go. So that's going to be 0.5108, and it's irrational. This one I can solve without my calculator. Just like, think, log of 10 is 1, right, because that's a base of 10. If I define the base of the log as 2, and I say, what's the log to the base 2 of 2? That's got to be 1. Log to the base x of x has to be 1, assuming x, of course, can't be 0. But, of course, the base and the argument can't be 0. We know that. That's a rule. So, really, using our log laws, all the same properties of regular logarithm are the same in natural logarithm. So I can take the exponent and turn it into a coefficient, which means that this is basically log to the base e of e, which is 1. Cool. What can we do with this C answer, or this C question? Well, let's see. We can change this from an exponential equation to a logarithmic equation. So I am going to say, all right, I'm going to take the log equation of this, which means that I'm going to say the base becomes 10, so I'll just say log, which is already a base 10. The answer is my argument, and the exponent is the answer. Everybody get how that equation became that? Again, if you need to, let's do a think. One of the first things we did in logarithms is learn that, say, for example, 2 to the power of 3 equals 8 get rearranged to log to the base 2 of 8 equals 3, right? The base goes here, the argument, the answer is the argument, and the exponent becomes the answer. And that's what I did to this equation, right? The base went here, the exponent became the answer, and the answer became the argument. And now I can just anti-log both sides of the equation. X equals 5. So if you understand how to do that with base 10 logs, the exact same logic works here. You can just simplify this to the natural log, because e is my base, so that's what that natural log means, of my argument is the answer. So x equals 7. Okay, so there's how logarithms work, or natural logarithms work. They work the exact same way as other logs. Now, let's do some algebra, the same as what we did with regular exponent equations. I'm going to take, since e is the base, instead of taking the log log of both sides, I'm going to take the natural log of both sides. And then exponents can, of course, become coefficients. But actually, before that, 2, 10, well, actually, yeah, maybe after that. I'll do this in 2 steps so I don't lose anybody. Ln to the base e is, again, that's like saying, how many e's do you have to count by before you get to e? And the answer is 1. So 2t minus 1, that's just times 1 is equal to the ln of 5. So 2t minus 1 is equal to the ln of 5. So t is equal to ln of 5 plus 1 divided by 2. And I already punched buttons on that, and I got 1.3047, blah, blah, blah. Okay? Okay, this one's a little freakier, because I've got like a double. This one's just a constant over here. This one is another variable. So, but I'm going to approach it the same way. I'm going to take the natural log. Because I see e, Right? You could say, well, hey, there's a 2. Why don't I take the log to the base 2 of both sides? I have no idea what log to the base 2 of e is, and my calculator would probably have fits trying to figure that out. But as soon as I see e, I'm thinking, I'm going to take the natural log of both sides of my equation. This will be easy. Then, once again, exponents become coefficients when you're in logarithm form. This thing is just 1. Let me get rid of that underline, but I was just trying to show you that that thing is 1. So that's x equals ln of 2 times x plus ln of 2. Collect my like terms, so I have x minus the natural log of 2 times x equals the natural log of 2. Factor out your x. And do a divide. And don't cancel those ln 2's. Those don't cancel. You got to punch buttons on that. So let's get the rabbit back. Come on, you. Wake up from your slumber. You are required. Okay, so erase that. So I would say natural log of 2. Don't forget to close the bracket or it's going to think it wants the whole thing as one argument. Divided by, open a bracket because we have to do the subtract before that divide, 1 minus the natural log of 2, close the bracket for the log, close the bracket for the denominator, equals, and that's what I got last time I did this problem, 2.259. Any questions so far? Notice the algebra here works the same way as regular logarithm algebra. It's just using a base of e and a new symbol for the log where we're saying ln because it's the natural base log because e is the natural base. All right, this guy. Whoa, okay, so what are we going to do here? I'm going to, again, take the log of both sides of the equation, the natural log, of course, because e is my base. And then I'm going to make this thing, right, exponents become coefficients. And while I'm at it, why don't I just say that this is, of course, 1. So I'm going to say times 1, which is just nothing. And then I can say, I will anti-natural log both sides of the equation. And then I'll do my algebra on that. 2y equals 10, y equals 5. Okay. Now, I haven't done this yet, but suppose I actually wanted to check this. Actually, let's see if there are any others. Maybe I'll find an easier one that I want to do a check on first. Yeah, let's do a check on this guy, because I still have the answer on my calculator, right? Right, Rabbit? You're still there? Yes, you do. It's still there. Okay, so I'm going to store that number. Now, again, different calculators store differently. I'm going to store into alpha A. So there we go. Enter. So there we go. That's now in memory A. I used the alpha button because you can see a little letter A there. So that means I think I can store into memory A, B, C, D, E, F, G, H. Actually, I think there's probably even more memories than that. But anyway, on your calculator, you might even have only just one memory. But one way or the other, I now have every decimal in this stored. Now, how do I get E on the calculator? Notice it's the opposite of the natural log. It's right there. So if you have an ln button, on every scientific calculator, shift of the ln button gives you this. So that's saying e to the what base. Now, if I just wanted the number e, I could just say, oh, okay, fine, just give me 1. There's e, ta-da, 2.71828. Again, that so looks like it's repeating, but trust me, it isn't. I would like to find e to the power of that number that I just solved. So I had that, where did I put that again? That's how good my memory is. I put it in A, didn't I? So recall A. Yeah, there, boom. And enter. Okay, so this side of the equation, doing my check, is 9.572. Blah, 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 blah. Now let's do the left side of the equation. Or sorry, the right side of the equation. I said I taught math. I didn't say I know my left from my right. 2 to the power of, open a bracket, go get that number again, recall memory A, plus 1. close brackets, you better be 9.572, I'm going to be mad. Yeah. There we go. Answer check. And you can do a check like that on any of these. So if you're ever hitting an answer key going, I'm not getting their answer, check it. It works. Oh, wouldn't y be 3? Where did I do something wrong? Wouldn't y be 3? 5 plus 5 is 10. What? Which number did you say y should be 3?
It's 2y minus 1, not 2y minus 5.
Oh, yep, you're right. That is totally a mistake. Thanks for being more awake than me. This is what happens when you stay up till 1 in the morning watching hockey. There we go. So that should be 2y equals 6 and y equals 3. So we should have done a check on that one. I would have realized right away it's wrong because the left and right sides would not have been the same. Actually, you know what? Now that I've seen it, I totally do want to do a check. Okay, let's do it. Let's punch buttons. Okay, so I want, this is going to be really complicated. Let's clear everything so we can see everything good here. Second function, e to the x. So e to the power of the natural log of 2 times 3 minus 1. I'm just going to put 5 because I know 2 times 3 minus 1 is 5. So I'm going to put a 5 in there. Close the bracket for the log, close the bracket for the exponent, and give me a 5. Yay, it works. Every once in a while you get a calculator that doesn't do that properly. Sometimes your cheaper like dollar store calculators, even though they have log buttons, you can't make that work. If you had a TI-30XA, I'm just holding that up to the camera here. If you have one of these, you can still do checks like that. You just have to start using your memory function. But it still does it. These things, these calculators, I keep making fun of them, calling them cheap, but they're actually really fine calculators. That they're just not quite as fancy as my rabbit calculator here. All right, next, one more algebra question, then we're going to do a word problem, and then we'll let you guys have some work time, and I'll go back and I'll answer that number 10B question that somebody asked about. Okay, so what are we going to do with this? Well, we are going to turn this into a natural log equation. And you might be thinking, but this number here isn't in a log. I can't work with it. Yes, you can, because you know, again, think. I think this is the third time today I've written think. We want you to think today. Think e to the power of, e to the power of 1 is e, because anything to the power of 1 is itself. So ln of e must be 1. So if ln of e is 1, I can change that 1 and express it as the ln of e. Then, since this is the same base, I can combine the arguments into a multiply. Oops, forgot the actual log. There we go. Now I can anti-ln both sides of the equation and say that x plus 1 equals e times x. That's just normal. Again, e is just a number. This is like saying x plus 1 equals 2x. In this case, it's not 2. It's 2.7818, blah, 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 blah. So I'm going to say that x minus ex equals negative 1 by rearranging the algebra. I'm going to factor out x. Oh, where would we be without factoring? The bestest tool in our toolbox. And then last step, x would equal negative 1 over 1 minus e. And again, how do I do that on a calculator? Okay, well, you got to trick your calculator into giving you e. Almost no calculators actually have just a direct e button. Press the button and there's e. You'd think they would. It's like, hey, there's a pi button. I don't have to do fancy steps just to get pi. But e is almost never directly on the calculator. Now, I say that, but I bet it is on here somewhere. I think it's in one of the math options or something. I don't care. I can find it super easy. I can say negative 1 divided by, open a bracket, 1 minus, oh, how do I get e? I just bring this function here, but I put an exponent of 1 on it, right? Because again, e to the power of 1 is just e. So I tricked the calculator into giving me e. Close the bracket, hit equals, and I think that's what I got last year. Yep, 0.58197. Blah, blah, blah. Want to give yourself a second and see if you can do that calculation on your calculator? See if you can get e and then work with it? I'll give you a minute. Shift and divide button. Really? Shift and divide gives me E on that calculator that I was using? Oh, I don't know. Is that really E? Are you E? You're right. It is programmed onto here. See, I never even knew that. A lot of calculators do not have E directly programmed in. You have to trick it. Like, for example, if I was using my, my TI-30XA here, I would, let's see, how do I get to E on here? I would go, okay, so on, I'll write this out. On a TI-30XA, to get E, you do the following. Type on your calculator 1, then type second function. That's the green button in the top left corner. And then hit natural ln. So 1, second function, ln, and there you go. Then the calculator should spit out 2.71828, blah, 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 blah. Okay, so that'll work. Try it, and then so in this case, in this button punch here, I'm going to put 1, hit a negative, divide by, open a bracket, 1 minus, put a 1 on the screen, shift, ln, close brackets, equals, and boom, I get this answer. So I don't need no fancy calculators. Good old TI, good old, like what somebody say, old reliable. Yeah, old reliable. You can take these things home and hammer nails with them; they'll still work. These are great little calculators, and they haven't changed much since I was in grade 10 or 11. The basic TI, although they're a lot cheaper than they were in those days. All right, let's do a word problem. There are 500 mice found in a field on June the 1st. On June 20th, 800 mice are counted. If the population of mice continues to increase at the same rate, according to this formula, remember I had you skip all the questions in the homework that had this formula because we had to see this example. P is the initial value, A is the final value. So P is how much your population is now, A is how much your future population is going to be, T is time in days, R is rate of increase or decrease, and we want to know how many mice there's going to be on June the 28th. Notice, if the R is greater than 0, then the function's increasing. If the rate is less than 0, the function's decreasing exponentially. Because, obviously, for radioactive decay, this R here would be a negative. Okay, so what we don't know is, we don't know R, right? What we do know is we know time in days is 20. We know P, the initial value, is, what's the initial value again? 500 mice at the start and 800 mice at the end. That's what we're looking for. Okay, so A equals P, E, R, T, PERT formula. 800 is 500 times E to the R times 20. What are we going to do? Step 1, we're going to divide both sides of the equation by 500. Step 2, we are going to take the natural log of both sides of the equation. Step 3, we use log law number 3. Exponents can be thought of as coefficients. The ln to the base of a number of itself is always 1. So my final answer will be whatever the ln of 8/5 divided by 20 is. You punch it and I'll punch it. This time I'll use old reliable. 8/5, close the brackets, natural log divided by 20 equals, and it should make sense that this is a decimal. Because what kind of a number are we finding here? A rate, a percent of growth. Right? So it makes sense that the growth rate can't be more, well, you wouldn't want the growth rate of your mice to be hundreds of percent. Unless you're growing mice. I don't know. Maybe you're supplying labs their mice. In which case, yeah, you want that high growth rate. Okay, next. That's not the end of the problem. how many mice will there be on June 28th? So now I know my R. Hopefully you didn't erase it. Hopefully it's still in your calculator. I go back to the formula. I know that I start with 500 mice. This time I now know that my R is 0.0235. And this time T is 28 days, right? Because first, so 28 days. 28 days later, the mice overrun us. So how many mice are we looking at? So I am going to take, I'm using old reliable here. So I'm going to take that decimal and I'm going to store it in memory 1. There, it's in memory 1. 500 times second function. Oh, no, sorry, hang on. I just messed that up. Okay, let's start that again. On old reliable, I'm going to take 500. That's a 5 and a 0, 0. Don't look for a 500 button. That's just button punch 500. 500 times. Now, on this calculator, you can't take the log of something until it's already there. So I'm going to have to get, so I'm going to put, open a bracket, and then recall my memory 1, because that's where I stored that number, and then times 28, close my brackets, and then take second function and ln. And then you should hit equals and have your right answer. Let me just try that. 500 times, open a bracket, recall 1 times 28, close that bracket, second function natural log equals. And yep, that gave me the right answer. 965 Mises. Those of you on a calculator more like my Wabbit, let me get the Wabbit out. Your button punch sequence would just basically be, well, first of all, you kind of have to get that first answer. Come on, go get me the first. Okay, let's go get the first answer again. What was it again? It was ln 8/5 divided by 20. So let's do that. So natural log of 8/5 divided by 20. And then this calculator, I don't really have to mess with memory. It remembers the last number as the answer. So I'm just going to have to go 500 times second function, natural log there, that's e to the power of, and then I just type in the last answer I got times 28 days, close bracket, equals, and there it is, 965 mice. Okay, so there we go. That's how those problems work. You can practice those now. Okay, I'm going to stop my lesson. Lesson over. Thanks for watching it.